We will discuss Weil's regularization theorem. Okay, and like in earlier lectures, there will be mostly statements and ideas and proofs, ideas of proof, but not too many details, because otherwise time would not be enough. And I think it's more important for you to get some kind of tools which are not necessarily in the toolkit of the birational geometer, in order to see them and be able to use them later if you need them. Okay. So first of all, I want to define what is the rational action of an algebraic group. So in this lecture, the round field will be algebraically closed, well, maybe of characteristic 0. And there will be an algebraic group G. And X variety. And, the first thing I'll do is to define a rational action. Of G on X is, as you guessed, a rational map. A, which starts from G times X and goes to X. That's like an action with rational maps. And now come two conditions. I will state them and comment later. So the first one is the rational map which goes from G times X to G times X, and which sends Gx to G and A of Gx would be dominant. I'll comment on this soon. Just write the second definition, second part of the definition. That the rational maps can look up two of them. From this triple product to X, you can do the following. You have a triple here. And you can send it either to G.H.X, and this dot notation will be just for like for actions. This is really shorthand for A of Gx. So you have this one, and you have the other one. You first make the product, and then act. And then they should be equal. Okay. I write it in this in a kind of brutal way, but this certainly deserves a comment, because the second condition is a natural one. If you want to define something like an action, right, it should be associative. But then in this rational maps, you implicitly compose rational maps. And you want to ensure that the composition makes sense. And here you need this, or you need something like this. And let me make a brief comment on this, because this is just checking carefully on the definition. So this implies that A is dominant, because you compose this dominant map with the second projection, which is a morphism, the surjective morphism. So it's still dominant. And then to define, for example, what is gh.x, what you do is the following. You start with multiplication on this thing, and then you do the identity on x, you land into g times x, and then you act, okay? So this is a surjective morphism, and this is a dominant rational map, so the composition makes sense. And the other composition makes sense for similar reasons. Okay, so that's why these definitions are in this order. And yes? This will come. Yes, it's a slightly non-trivial consequence of this. And actually, I copied this definition from a paper of de Mazur, which is a very remarkable paper. Subgroupe algébrique de rang maximal du groupe de Cremona. And he really makes some foundational material on rational actions. And then he goes on to define toric varieties, which is another business. But anyway, so this is a kind of weakest set of axioms for rational actions, from which the other, maybe more standard definitions are deduced. Okay, yes? No, this will come next. Maybe I'll answer all kinds of natural questions by a lemma, which is also in de Mazur's paper. So let me denote by V. This will be the domain of definition of A. This is just the largest open subset where this map is defined. So now you get a honest morphism from V to X. And what you can also do, given G in G, you can consider Vg, which is the intersection of V with G times X. The natural thing to do if you look at the action of a single element. And now comes a lemma, which is also due to de Mazur. Which says that, first of all, while Vg is dense, clearly open, you can see it in X by just taking the second projection. So I will just see it in X. So now you get, indeed, a honest map from Vg to X. And the second part of the lemma is E from VE to X, is just the inclusion. Okay, I think this probably answers both questions. And I will not prove the lemma. It's just a manipulation of rational maps, rather clever. I will just mention the consequence of this, which is also due to de Mazur. The first one is that this map, which was in the first definition, which is actually third projection comma A, is actually birational. Which is maybe the standard way to define rational action. So another consequence is each AG is birational. And a third consequence, which is also very practical, is that you can rephrase this second condition in a much more concrete way. So if you have 3 points, 2 in G, 1 in X, and Hx and GHx are defined in the sense of rational maps. So the action maps is defined at this point. Then gh.x is defined and equals so you can have these identities as you whenever they make sense. Okay, so these are again not quite trivial consequences of the definition, which are maybe explained in detail in the notes. So I'll just use them for safety. This kind of thing is very tricky to to do in a blackboard and takes time. But anyway, it's good to know. And this is really some very practical way to think of an action. You just have this. And now I can state Weil's regularization theorem. So you have a rational action. And the statement is that there exists birational isomorphism f from x to some other variety y, such that and an action E such that some diagram commutes. I think you guess which one. Yes. And this should be I times commutes. Okay, so that's the statement, which probably already mentioned, and my A is not so nice. So this means after conjugation by F, you transform your rational action into a honest action. In the literature, you see regular action. I will just use action. Personal reasons. Okay, so this is really a key result for rational actions because it reduces these two problems on automorphism groups. And for automorphism groups, at least for projective varieties, we know something. But now this Y is not projective in the statements. It's just an abstract variety. And you will see in the proof that it's just constructed as an abstract variety. So at this stage, we would like to make some additions to this theorem to put some additional conditions on the varieties. Well, what you can always do is assume X smooth. because you can replace X by any birational equivalent variety, for the smooth locus. And then you can also assume that Y is smooth, because again you replace it by the smooth locus, and which is certainly stable by any automorphisms. If you want a formal proof, you play the game of the day before yesterday with commuting with smooth morphisms. So that's what we can do at this stage, and after some work we will add the words projective at the end. And this will take us the whole Friday, so, well, okay, I mean 2 lectures. Anyway, so now I will mention a little bit of history. This is due to Weil. Again, for G connected. And as already mentioned, this was soon generalized by Rosenlicht. And this is not, well, there are many other things in the paper by Rosenlicht, but that's not the deepest one. Weil's proof is quite remarkable and extremely hard to follow, because it was written at the beginnings of foundations of algebraic geometry in a language which has completely changed. And also Weil's paper is kind of its own. For example, there is no statement, and you don't know where the proof starts. And, but still, there are extremely nice ideas, because he does everything out of nothing. There was no, like, just basic definitions which are kind of implicit, or you have to guess. So this was over an arbitrary field. And we will see in a moment that even if we start with an algebraically closed field and try to prove this statement, at some stage we have to go to some other fields. So is a good reason. But Weil's original proof was rewritten and clarified by a person called Zaitsev over C, and Kraft over algebraically closed field. They explained in modern or clear languages how the original ideas of Weil can be rephrased. And that's a very substantial work. And the proof I will present is taken from my paper. It's called like this. And it's different and uses more advanced tools. But I think these tools, which well, already existed, are rather interesting on their own. So that's why I'm presenting this. Well, now I will present the main step of the proof. And again, it will be very sketchy. It begins with a special case where the action is B acts on X, maybe almost transitively. In the sense that the map from G times X to X times X, which sends any pair to maybe Gx and X, okay? This map is dominant. So I will write it again in a kind of abstract sense, and you have to figure out what this really means. This means if you have any 2 points, Y and X, general, you find some element of the group which sends the second one to the first one in this convention. Okay? That's exactly what it means. Maybe I write it. For general X, Y, and X exists G and G, that Y equals G dot X. And implicitly this makes sense, okay? So you have to add this kind of conditions. Okay? So that's a special case which is actually in de Mazure's paper. In this situation, the action is indeed regularizable, and the reason is you have a candidate for the variety you want, which is just some kind of orbit, homogeneous space. So you have to make sense of this orbit. So you take X in X general, and you consider the orbit map AX and then the Mazur shows, I will not do it, that this can be defined on some open subset. Defined on W, X, G. These are not the notations of the nodes, but not so important. And you may, well, it's defined at the identity, right? Because of what we just said. And so you can take its fiber at the identity. This is so it's just some locally closed subset of G, and you take its closure. Ah, sorry. Okay. Take the fiber which contains the identity, which is a candidate for isotropic group. And then the statement is the closure of this in G. Let me call it Gx. This is a closed subgroup. And now what you have is that the map here is Gx invariant. For the action by right multiplication. And so your map AX factors through a map from the quotient to, okay. This is just a rational map. This is certainly equivariant because G acts on it by let multiplication, so orbit map is equivalent. And what the measure shows is that this map is generically injective. And now you pick up your point that the map, orbit map is dominant, which comes out of this condition. And since we are in characteristic 0, this map is birational. In positive characteristics, you would have lots of trouble, but just ignore this. And so you get a regularization. Okay? So it looks like a cheap proof, but if you do it carefully, you need need some work. Yes. Thank you. So here, again, you have a natural candidate after some work for the linearization, and it works. Okay. The next step is to reduce to this almost transitive setting by some rather classical trick of going to the orbit space. Well, we use almost transitivity. That's the map is dominant. Okay. Otherwise, you just have an orbit, but you don't have the full picture. Okay. Okay. So the second step is let me call it rational quotient. Well, here again is not a well-defined object to start with. We want to construct some orbit space in general. And orbit space is in algebraic geometry often constructed indirectly with invariant functions. For example, for invariant of finite groups, you just take invariant regular functions. Here we have rational functions, so what we will do is consider the function field of x, and inside it the subfield of invariant functions, which is by definition the set of functions that f of Vx is f of x for all g in G, such that Vx fine. And f is defined as this point. Okay. This is an action of an abstract group on this field. So it looks like a bit like Galois theory. And by what we saw in the first lecture, this L is a finitely generated field. So we see that L is a function field of some variety y. Sorry, that's not the final y, but I'll use this one, otherwise I'll get confused. Maybe you sorry. Anyway, so y just some intermediate variety which has nothing to do with the final one. And this field inclusion gives us a map, rational map from x to y, which is by construction a dominant. Okay, and it's also G invariant. by, again, the definition of the subfield L, right? Okay, so now we are free to replace X and Y with appropriate open subsets. And so we may assume this map is as nice as we want somehow. So we may assume maybe X, Y smooth, pi to be a morphism, and even a smooth morphism. This is by generic smoothness, which works since we are in characteristic 0. And now we consider the same map as over there. But then the observation is this lands in the fiber product. So the pairs which are sent to the same point in Y, because this map is invariant. Okay? And this fiber product, by our assumptions, is not too bad. This is a smooth variety. Because it's obtained from X by a smooth morphism. Let me explain. It's just abstract nonsense, sorry. Smooth. And now the claim is that this map is dominant. Actually, this is due to Rosenlicht. I will not prove it. It's really an algebraic statement, because you have to prove that at the level of coordinate rings, this is injective. And this looks like algebraic exercise on field extensions, which is done in my paper because I needed it, but it's really not a deep fact. Still, that's the main point somehow. Okay, so at this stage, we will make the same kind of manipulations than in Evgeny Schindler's lecture and go to the generic fiber. So in order to get to something over a field, not over Y. So this, I should maybe stress that these objects can be viewed over Y. This is comes from the definition of fiber product, and this is a projection through X to Y. So let's take the generic point. Of Y. So by definition, this field, residue field of this point is K of Y, which is L. And let's consider everything over this eta. Well, first of all, I will put GL, because G is not over K of Y. G is a K group. I can make an extension to any larger field, extension of scalars, and this will be my GL. And then come this action map over here. Then come X eta. This is a generic fiber. And I go to X eta times L. Okay. That's what happens over Y, eta. And this is still dominant. It's still a rational map. Yes, thank you. Thank you. But well, this looks like a homogeneous variety, almost homogeneous variety. That was the definition of almost homogeneous variety. Transitive. Almost transitively. Okay. And so you can regularize this action. Together with a birational morphism to X eta. Okay? And I must say here I'm cheating horribly. And it seems some of you should have seen that I'm cheating. Because you see, in the definition of almost transitive actions, I worked over an algebraically closed field, and so I chose some base point, which is over this field. And here I'm in a variety which is L variety. Maybe it has no L point. And sometimes this occurs, and you saw this in Evgeny's lecture. You have curves of genus 1 which have no rational point. So we have to deal with this. And the way we do this is, well, maybe I'll sketch it here. So if this X eta has enough L points, I mean, enough means some L points such as the orbit map is dominant. This is the argument I just gave, and otherwise, there is a standard trick in this situation. You get some points after some finite extension. Okay, because you work with schemes of finite type. They have all their closed points are defined over finite extension. So there exists a finite extension of fields. This L is a function field. Okay, and that's it. with lots of variables. Okay. That this X eta base change to H prime has enough L prime points. Okay. Now I can make this extension a bit larger and assume it's Galois. Because I'm in characteristic 0, so all extensions are separable. I can take the Galois closure with group, I don't know. And then what I have is the following. I have a regularization at this level after L prime. This will be a GL prime regularization. And I want one on X eta. And here, because it's a base chain, I have a map. And actually, this map is quotient by the Galois group. This is kind of standard fact of Galois theory. And this comes from the fact that the map from spec L prime to spec L is a quotient by the Galois group by definition, right? And now this is obtained by base change. So now I just do the same here. And by standard properties of quotients, I get this. And well, here I have to use some tool which is called Galois descent. You have a variety over L prime. Want to descend it to a variety over L. This works if the variety is quasi-projective, because you have to take the quotient by a finite group. So you'd better have that the orbits are contained in open affine subsets, and this holds if this is quasi-projective. And actually, it's a known fact that homogeneous spaces are quasi-projective. So here this works. It's not a trivial fact, but it's you can find it in a book by, for example, Milne. Okay. So at this stage, we don't have a full regularization. We have one after some kind of strange localization when you replace this y by its function field. And so the final step is kind of a spreading out argument, like in Evgeny's talk. We have something over a function field, and we have to enlarge it a little bit to something over a honest base. And the way it works for G linear is rather simple. So now I will assume G linear and explain how you deal with this assumption a little bit later. What you do is you can embed this variety, which is an L variety, into some projective space over L, and compatibly with the action of GL, which should act on this Pn by some homomorphism. Here I will put some GL n plus 1 L for some reasons. So the claim is there exists a homomorphism of L groups and immersion, which are compatible in the obvious way. So again, this is something I mentioned earlier. This is Chevalier's theorem if you have an L point, because you embed a homogeneous space in a projective space. And otherwise, you also use this trick of Galois descent. And out of this, we can finish the construction, because we just put all the coefficients we see in some big ring, which will replace our function field. Well, in more details, you do this as follows. You have matrix coefficients of rho. These are functions aij, the coordinates of this matrix, which belong to O of G L. Okay, which is by definition O of G tensor K L. Well, to get some, I mean, you also need the determinant of this matrix, G, which also belongs to O of G, and so. And these are finitely elements of this tensor product. So by taking the L parts, you get finitely many elements of your function field. You just put them in a big ring. Okay, so R, ring, K algebra, containing such that this ARG and also the inverse of D belong to O of G tensor AR. Okay. That's and you need that the fraction field of R is L. This can be achieved by just adding further finitely many elements. And now you have your morphism here, which is defined over R in some obvious sense. So you just write this more explicitly. So you write Y to be the spectrum of R. Which is, of course, an affine K variety. This algebra, well, sorry. Forgot the finitely generated. Otherwise, we'll be in trouble. Now, well, you just get, by construction, you get a rho Y, which starts from now G times Y, to G ln Y. Well, you can think of it as GLN with coefficients in R. Okay, and what you get is Z, which is again in P n L, and this one sits in P n Y. Because actually the spec L is a generic point of this Y by just construction. And now you just take the closure of this inside by the way, this is just Pn, the usual one, over K, times Y. There's no mystery there. And now what you see is this action of this group scheme stabilizes this W. So what you get is some map like this. Okay, this is just the action of this group fiber-wise. But now the observation is this is all over Y. Projection is fixed, and as you guessed, this is just G times the formal thing on the fiber product. They cancel, and so you get an action, and that's it. Yes? Yes, you're perfectly right. Sorry, I got lost with all my letters. Let me. And you see that over the generic fiber, this W is just this original Z, so it's really birational to the one we started with. So, well, that's a proof modulo key point that we assume G linear. Okay, how much time do I have? Ah, well, that will be a very hard task, but I'll begin to do something, and maybe I'll continue in the afternoon, because yes. Mm-hmm. Yes. Yes. Yes, but this comes out of the construction, I think. Okay. So this is just the action map, homomorphism from G L prime to this given by some. Okay. You're right, but I think it's not a problem. Right. I can fix it. Okay, so now I'll complete the argument by independent proposition. Which says the following: if suppose X is say rational and A faithful rational action. I'll explain this word. So faithful means that if you have a non-trivial element, it acts non-trivially. Okay. So you get morally a subgroup of the Cremona group, and then X is linear. The G part, sorry. Okay, that's a statement I mentioned in the question session yesterday, where I have only a very indirect proof, which will last more than 5 minutes. But the thing is, this also works for rationally connected. The arguments only use rational curves. And so I will start the proof of this and continue in the afternoon. There are two main ingredients. The first one says that isotopic groups are linear, tend to be linear. So if, well, under these assumptions, well, maybe I'll state it in a different way. So suppose you have acts regularly on a variety X, and, well, faithfully, sorry. And X is any point, then the stabilizer of the isotopic group is linear. So that's a really key point in this theory of algebraic transformation groups. It's not a deep fact, but it's extremely useful. And the second ingredient, which needs more room, This one is a very natural candidate, but it's infinite dimensional, and it's not a union of finite dimensional subrepresentations. So what you have to do is take the local ring and mod out by powers of the maximal ideal, and then you get it. So, well, maybe by lack of time, I just mention the second ingredient, and then we'll see what happens next. Yes. Yes. Otherwise, you have certainly many counterexamples, right? So the second ingredient is called Chevalier structure theorem. Which says that if you have a connected algebraic group, then there is a unique exact sequence. There is a linear part and an abelian variety part. So this is an abelian variety. And this part is connected and linear. Okay. This is not an easy theorem. Well, it's not proved in any textbook on algebraic group. So you see only in papers. But in the notes, you will find references to 2 papers by Conrad. And also Rosenlicht. Which proves this theorem in very different ways. Anyway, it's a very important fact because you see every algebraic group is built from 2 separate pieces. And if you remember, there are no homomorphisms between any of these pieces, so this makes the sequence unique. So I think it's time to stop, sorry. And, thank you for your attention. Yes? This just to make my life simpler. Well, in positive characteristics, what you prove in addition is that this field extension is separable. And let me remind you, this is Kg, and this is really some statement of Galois theory, right? For G of finite group. Something you learn in Galois theory, and the proof is a version of that for Galois theory. And it's due also to Rosenlicht. Once you have this, you see that the quotient morphism is generically smooth. And so this makes this more reasonable. Okay? So I didn't cheat completely at this point, yes? No, just shrink. Yes, just remove every bad thing. No, I don't use any resolution of singularities. For the morphism to be smooth, I use generic smoothness in characteristic 0. And you just remove, I mean, on the source, you can remove everything, except, well, almost. And this argument gives you a substitute for generic smoothness in positive characteristics. Okay? Yes? Yes? Actually, yes, but These are open varieties. These are open varieties, they are not projective. And by nature, because as we just did, we started with something and we just make it smaller. So peak zero is kind of a mess. And then even the action of G on peak zero is hard to control, because you have an algebraic action if you work with projective or at least proper schemes. Otherwise, you don't know. So all this proof avoids peak zero or hides it in some other corner, okay? Yes. Mm-hmm. This is much easier. Yes, yes. In this setting, this can be proved in a more natural way than the one I will present. Yes, with peak zero. You just have to indeed to assume that peak x is discrete, and you get it. Yes, but again, I don't know how to reduce to this case, because I cannot yet compactify my in an equivalent way. So. Yes. That's the idea, yes. Actually, the proof of Conrad uses more or less, well, the proof of Rosenlich, sorry, uses the Albanese morphism, which is a universal morphism to an abelian variety, which is exactly this one, by what you said. That the thing is, this Gillen is rational, actually. So that's really the immersive vibration. But again, this theorem is valid over any perfect field. And immersive vibration, I'm not so sure. Thank you.